In this video we have 5 problems involving limits. 3 of them involve rational expressions. So again, we remember that when we look at the limit as x approaches a particular number, in this case x equals 0, x equals 1, x equals 3, or in this last two it's h approaches 0. Easiest way to determine if you have a limit is to just plug it in. And if you get something like 0 over 0, or something that's not defined, you could say 1 over 0, then the limit's not going to exist. So what you want to do is plug it in. So look at the first one. Limit of this rational expression as x goes to 0. So what do we get if we plug in 0 for x? Well, in the numerator we had 0 squared plus 3 times 0, that's 0 over 0. So we get 0 over 0. That's called an indeterminate form. So in some of these cases we had to use other techniques, algebra, for example, to simplify it further. So what you want to realize that as the limit approaches 0, it doesn't have to get to 0. If you plug it in and you get a number over a number and it's defined, fine. But in this case we don't. So what we do is we factor an x out of this. You get x times x plus 3. So now what we look at is, as x goes to 0, what does this expression approach? As x gets close to 0. We're going to assume it doesn't get to 0 because we don't want to divide by 0. So let's divide this out. X is close to 0. So if x does not equal to 0, we can cancel the x's and we get x plus 3. The limit as x goes to 0 of x plus 3. So we just simply say as x gets close to 0, x plus 3 gets close to, well, 0 plus 3. So this will be 3. That's it. Now in number 2, we'll find the limit of this expression, this rational expression, as x approaches 1. So again, if we plug in 1 where the x is, in the numerator we get 1 squared minus 1, that's 0. Denominator, 1 minus 1, that's 0. 0 over 0. So again, that's indeterminate. So we got to get another look at this before we can determine the limit. So what we do here is say, okay, we're going to let x approach 1, but we don't want it to get to 1. That way, x minus 1 is not 0. We're not dividing by 0. We're dividing something close by something close to 0, but not quite 0, so those cancel out. So what do I have left? Limit as x goes to 1. Again, the x minus 1 cancels, I get x plus 1. And basically what we're doing here is just plugging it in. Now that we get another look at it, because we say as x goes to 1, x is 0 close to 1, then x plus 1 gets close, very close to what? Well, 1 plus 1. So the limit is 2 for this one. 2, and for the first one, 3. In the same way, for the third one, we want to find the limit as x gets real close to 3. So let's just plug it in. 3 squared is 9, and then a minus 3 for that x, and then a minus x. That's 0 on top, and then 3 minus 3 in the denominator, that's 0. Again, we get an indeterminate form. That means we're not able to come up with a solution there. But try to factor this out. So well, let's factor it out. X squared minus 6 factors into x minus 3 and x plus 2. So we want to find the limits as x gets real close to 3. It doesn't have to get to 3. So in that case, I know that x minus 3 is not going to be 0. I can divide that out. So I get another look at this. The limit as x goes to 3 of x plus 2. So now, as x is close to 3, x plus 2 is close to, well, 3 plus 2. The limit of this one is 35. That's the limit. Now, if you have something like this, now this one says compute the limits that exist. Well, in this one, they're all going to exist. So let me give you one where it doesn't exist. I say when I find the limit as x goes to, say, 5, 3 over x minus 5. So here, if I just plug it in, I get 3 over 0. 3 divided by 0 is not defined. Limit here does not exist. There is no limit. So there's nothing I can do in this particular case. You would look at the graph for this expression. Of course, you have a vertical asymptote at x equal to 5. So let's go to the next one here. So let's look here. Okay, now on this one, number 4, we have the limit as h approaches 0 of 3 plus h squared minus 9 over h. So again, look, if I plug in 0 for the h's, I get, this is just 3 squared is 9, minus 9 is 0, and put a 0 here where the h is, I get 0 over 0. Again, it's indeterminate. So here what we'll do is do some algebra. Let's see, let's square this out. 3 plus h squared will give me a 9 plus double the product of 3 and h is 6h, and then plus h squared. minus 9. We get another look at this. We do some algebra and see if we can determine what the limit is going to be. So here's what happens. The 9 here and the minus 9 here is going to cancel. So I'm left on top numerator with 6h plus h squared, and that's over h. Now this one is like the first 3 now, because now if I plug it in, I got 0 over 0, because I got h and h squared and h in the bottom and h is 0, so I've got to get 0 over 0. But it's just one again where I can factor. So what I do is I want h to go close to 0 but not get there, because I want to divide out that h. So factor out the h here and I get 6 plus 8. We say h approaches 0 but doesn't quite get there, so I can divide this and this out. And I got now 6 plus h. So this is the limit then, as h goes to 0, of 6 plus h. Now another look at this. The limit of 6 plus h as h gets close to 0. Well, as h gets close to 0, 6 plus h gets close to 6 plus 0, so this is going to come out to 6. There we have it. That's your limit. A little bit different than the first 3, but the same idea. Now let's look at number 5 here. Again, if I just plug in the 0, with the limit as of this expression, this radical expression here, plug in a 0 where the h is on top, I get the square root of 2 minus the square root of 2, that's 0, and then I put a 0 where the h is, 0 over 0, again, indeterminate form. So I can't really factor here. So this is just another technique. And there's more advanced techniques that you can use to evaluate limits. On this particular video, we're using mainly algebra. So this is what I'm going to do. I'm going to multiply here, the numerator, because the way it is, I get 0 over 0. So I can't tell. Okay, you can't tell what it approaches. But a little trick that you can use is I'm going to multiply by the conjugate of the numerator. In other words, the square root of 2 plus h. In other words, this is a minus b. And if I look at a plus b, all I'm doing there is taking the opposite sign. Same two terms, a and b, but minus. That's the conjugate. So in this case, I have a minus, so I'll make this a plus here. So I'm multiplying the numerator and denominator by the conjugate of what I have in the numerator. And that's legal because all I'm really doing is multiplying by 1. You multiply anything by 1, it doesn't change it. So it's just another way of rewriting this. There you have it. This over this is 1. So now, come over here and say this is the limit as h goes to 0. So multiplying the conjugate here in the numerator, radical 2 plus h minus radical 2 times this conjugate. It says a minus b times a plus b is a squared minus b squared. So this is just giving me 2 plus h because it squares this. You square it, it gets rid of the radical. And then it's minus the square of radical 2. That'll give me 2. And then I got an h. Now in the denominator I got h there times that conjugate expression. Give me the square root 2 plus h plus radical 2. And then we simplify this. So 2 minus 2 cancels. That gives me 0 there. All I'm left is the h here. And now I'm taking the limit as h goes to 0, but I don't want h to get to 0 because I don't want to divide by 0. So I get it real close. I'm allowed to divide this out. And everything cancels out in the numerator except the 1. And the denominator, I got this expression right here. So let me just rewrite this or delete this out. So these canceled out. This h here divided out. And then I get a 1 here. Now I can take the limit as h goes to 0 here, and now I can just plug it in. So what do we get if I plug it in? H goes to 0. This h here and this radical goes to 0, so I get radical 2 plus radical 2. This is 1. So basically I get 2. Radical 2 plus radical 2 is 2 radical 2. So I get this right here. And usually we rationalize. If I multiply the numerator and the denominator by the radical 2 here, I get radical 2 up here. This would be 2 and 2. This would be a 4. So either way, either this way, or if you want to rationalize it, which you probably should, that right there. Now one thing to consider is this here, and I hope you notice this result here. Problem number 4 is considering this function f of x is equal to x squared If I take the derivative of this using the regular formulas, the derivative of this parabola f of x equal to x squared, prime here, and then the derivative of x squared is 2x. Okay, that's the derivative. If I evaluate this derivative at 3, I would put the 3 there where the x is. 2 times 2 is 6. I get a 6. Okay, we had it over here. That's all this is doing here, problem number 4, except it's using the definition of the limit of the derivative. If you think about your formula for f prime of x, in terms of a limit, the derivative is given by this limit. The limit is h goes to 0 of f of x plus h minus f of x over h. So if I use this definition here and just compute it, I get the formula for the derivative. And if I plug in 3, I get the answer that we got over here. So if I put, instead of an x here, I put a 3 right here. This is the x. This 3 would be the x that would go here. And then it's plus h. And then the square, of course, comes from the function. And then minus f of x. That'd be 3 squared. That's 9. So we're just using the definition of the derivative to compute, in this particular case, the derivative at the point where x is equal to 3. Now we're doing the same thing for 5, except we're using another function. So notice, for number 5, the function I'm working with is f of x equal to the square root of x. So if I use the limit definition on this radical function here, I would get this, f prime of x then. I was finding the derivative of the square root of x, and this would be x to the 1/2. Another way to write the square root of x. And then 1/2 in front is 1/2 here. And then I subtract 1 from the 1/2, I get negative 1/2. And I can take that to the denominator, just change the sign, so this would give me a 2, x to the 1/2, or I could write it this way. So if I left the, instead of a 2 here, I had the x, and I would go through all this procedure here, I would get the derivative in terms of x right here. And so what we're doing is this. The derivative at the point where x is 2, plug in 2 right there where the x is, and that gives me 1 over 2 times the square root of 2, which of course gives me the answer we got. So anyway, hope you could see that. All we're doing is computing the derivative of a particular function at some value in the domain of that function. In number 4, it was the function f of x equal to x squared. In number 5, it was the function f of x equal to square root of x. Just a little something extra there. Thanks for watching. We'll see you next time.